Okay, last time we were talking about how to build a simple CMOS memory circuit out of transistors, and we had wound up talking about a transparent D latch. Actually, we talked about, I guess we called it a level sensitive D latch. And we drew that kind of at a gate level as a box with a D input, a Q, and a Q bar output, and some sort of clock input. And the basic idea was that when clock signal phi is 0, the latch ignores D and remembers its state. When phi goes high, when phi is equal to 1, the latch reads, copies, or let's say copies, the latch sets Q, say D becomes Q. How about that? D becomes Q with some slight delay. I'm not sure I used this terminology last time, but this is called typically the transparent phase, or this is the opaque phase of the latch, where the latch is not allowing anything to flow through it. And this is sometimes called the transparent phase. Of the latch. So basically the idea is when the latch is in the phi equals 0 or low state, it's opaque, nothing goes through it. When phi is high, it's in the transparent phase, D just flows straight through it with a little bit of delay. Sometimes the latch is said to be closed in this phase, and sometimes the latch is said to be open in this phase, kind of like the window blinds. If you open the blinds, the window is transparent and lets light in. If you close the blinds, the window is now opaque and you can't see through it. It's kind of like that. And in this type of latch is what we talked about last time down at the transistor level. You can build one of these things with a pair of cross-coupled NOR gates and add on sort of a clock device in series with RNS, and then you basically feed D and its complement into S and R, and you get this structure. I want to talk about now how we can make what's called an edge-triggered flip-flop from these things. So an edge-triggered flip-flop is very similar in concept to a D latch. In fact, we often will draw it with pretty much the same symbol. So it's got a D input, a Q, and a Q bar output, and it's got a clock input. But in this case, it's only on a clock edge that D gets propagated to Q. And so you can have a rising edge triggered flip-flop, for a falling edge-triggered flip-flop. And so a rising edge triggered flip-flop basically propagates D to Q when the clock edge rises from low to high. And a falling edge triggered flip-flop is one where D gets propagated to Q on the falling edge. So rising edge, falling edge. And these are typically the type of devices that people will use when designing digital systems, at least for the most part. And you can actually build edge-triggered flip-flops in a variety of different ways. We're going to talk about one simple arrangement, which is called a master-slave. Master-slave approach. Perhaps not the most politically correct designation, but that's what it's called. And the basic idea here is we're going to have two D latches, two transparent D latches, the clock inputs connected together in cascade. And the basic idea is that we're going to feed the clock signal phi, let's say, into, let's first feed it directly into the first latch here, and then we're going to feed complement into the second latch. So we'll have a D input to the whole thing, a Q output, and a Q bar output of the whole thing. And let's think about what happens. So when phi is, let's say phi is equal to 0. Well, this first latch is opaque. So it's basically ignoring its input until phi goes high and we enter its transparent phase. And so let's suppose D is doing something like this. And let's call this signal maybe D prime. Well, D prime, we're not quite sure what it's doing because we don't know what the initial state is here. But let's assume that the initial state is low. So D prime is going to be low until D goes high. So at this point, when D goes high, this first latch is now open and it's allowing data to go through it, and so this is going to go high. Well, the second latch, when we're in the opaque, when we're in the transparent phase of the first latch, is in its opaque phase. And so D prime is not going to propagate through to Q, the overall output here, until phi goes low. Phi bar then going high will allow D prime to go through. The basic idea here is that we have a master latch and a slave latch, and the idea here is that the master latch is going to sample the input when phi is high, and the slave latch is going to basically ignore what's going on while the master is sampling. But then when, in this case, when the clock goes low, the master closes off its sampling of its input and has a steady value for the slave latch to adopt. And so in this case, when the clock goes low, that's when Q goes high. That's when D is propagated to Q. So this would be a falling edge triggered. Maybe I should draw this up here. Falling edge triggered. There's a falling edge triggered arrangement. And like I said, the basic idea is the master latch is sampling the input during its transparent phase, and then it becomes opaque, and at that point, when this becomes opaque, this one becomes transparent and samples a steady input that's not changing. And then when this one becomes transparent again, this one becomes opaque and remembers that last value until this one closes off again, and then this one takes the new sampled value. The final sampled value when phi goes low is what the slave latch adopts. Well, how could we make a rising edge triggered flip-flop? That's actually pretty straightforward, because all we have to do is change the phase of the clock, sort of flip the phase of the clock. So we can make a rising edge triggered flip-flop using this kind of approach by simply changing where we put the clock and clock bar. So if we instead put the clock inverter here, call this D prime. Well, in this case, when phi is low, that's when this first latch, the master latch, is sampling the input. And then when phi goes high, this latch closes off, the master latch closes off, and the slave latch then starts sampling its input, D prime, which is now being held constant by the master latch. And so it's at the rising edge of phi that D is going to be propagated to Q. And so basically from two transparent latches with a suitable clock inversion, we can actually make an edge-triggered flip-flop. Now, it's also possible to do other things, like for instance, we can take our transparent latch that we talked about last time that had the cross-coupled NOR gate with the extra transistors in it for the clock. So we could have something like so there's a cross-coupled inverters. have our R and S. Inputs, and we have our clock. So this might be, say this is D and D bar. Let's see, this is phi, and this might be Q bar, and this might be Q. So there was this version of the latch that we talked about last time, only we had R and S, but if we feed D and D bar in here for R and S, then we get our D latch. We could make an upside down version of this, which is basically exactly the same topology, except we replace ends with P's and flip the connections of ground and VDD to basically make something that looks like this. So there's our cross-coupled inverters. Only instead of having what amounts to cross-coupled NOR gates, we can have what amounts to cross-coupled NAND gates. So this is our clock input. And then we have our series transistors that correspond to these guys here, BPMOSs. And then this might be and I could have this wrong, but we either put D, we call D prime in here, or I guess I should say D, and D bar. And then this is probably Q bar and Q. So this is sort of the upside down version of this. And like I said, I could have the D and the D bar switched here, given what I've called Q and Q bar. I forget exactly what it is at this point, but this would be based on the cross-coupled NOR gate version of the RS latch, which we talked about before. Well, this one is based on cross-coupled NAND gate. So if you ignore the clock transistors, let's suppose the clock is high, you basically have here the Q from the other side being NANDed, so with D, and the pull-up here would be the parallel combination of these two PMOS transistors. And so this would be a structure based on a pair of cross-coupled NAND gates. something like that. And we said that this one was also an RS latch, but it was active low. The two inputs were active low instead of being active high. Well, given that we're talking about a D latch instead of an RS latch, the two inputs R and S are basically always complementary in this arrangement anyway. And so whether the inputs are active high or active low sort of doesn't matter in some sense. But the key thing here with respect to the master-slave arrangement that I'm trying to bring out is that this latch is transparent when phi is high. This version is transparent when phi is low. And you can convince yourself of that because here D and D bar are in series with the clock down here in the pull down. And so these transistors allow D and D bar to affect the outputs of the latch when phi is high, and these N transistors are on. Well, over here in the upside down version of the latch, we have these clock transistors in series with the D and the D bar transistors up here that will set the state of the latch or write a new state into the latch when phi is low. And so we can use a complementary pair of these types of D latches in our master-slave arrangement, and we don't have to do any clock inversions, which is super cool. So we don't have the delay through the inversion of the clock. So anyway, I'm not sure that point makes a whole lot of sense to people at this point, but I figured I'd tell you about it anyway. Anyway, so that's how we're gonna leave it for making an edge-triggered D flip-flop from transparent latches. Like I said, there are other approaches, but they tend to be, from my point of view, maybe a little bit more risky than the master-slave approach. I wanted to go back and revisit another topic that we had talked about before, and that is when we talked about CMOS logic gates, we mentioned that combinational gates were ones that were always driven either high or low by the pull-up or the pull-down network. And I mentioned that there was a type of gate called a state-holding gate. And I wanted to show you an example of a state-holding gate. And we're just going to talk about one example. It's actually quite a useful example. And here is the basic structure of the gate. It's got two transistors in the pull-down network and two transistors in the pull-up network. Call the two inputs A and B. And we're going to have an inverter here to generate the actual output of the gate, which we're going to call Y. And so it's obvious that we've got these two transistors here in series, and we've also got two transistors in the pull-up network in series. And so the pull-down network conducts when A and B are both high. So pull-down network when A and B. So the conduction conditions for the pull-down network are AB. Pull-down or pull-up network conducts when not A and not B, which is equal to, by De Morgan's law, A nor B. So if we were to draw a truth table for this gate, might have A, B, and Y. So we have four combinations, 0, 0, 0, 1, 1, 0, and 1, 1. Well, when A and B are both high, then the input to the inverter here, which I guess we could call Y bar, since the output of the inverter is Y, gets pulled low. Well, if that gets pulled low, then Y goes high. Y bar is going to be pulled high when A and B are both low, which is this row in the truth table. So Y bar becomes 1 when A and B are both 0, and so Y would then be 0. What about the case when A and B differ from each other? So when A is 0 and B is 1, or when A is 1 and B is 0. Well, in both those cases, let's take this case here. When A is 0 and B is 1. Well, when A is 0, this transistor is off. This transistor is on. This transistor is on. This transistor is off. So we have one transistor on and one transistor off in series in both the pull-up and the pull-down networks. So in this case, both pull-up and pull-down network are completely cut off. And so what happens? Well, whatever previous value Y bar had will be maintained. It will hold its state. And it will hold its state by just, in this case, whatever charge happens to be stored on the parasitic capacitance associated with this node, the two drains of these two transistors, the two gates of this inverter, and whatever wiring capacitance, or whatever capacitance there is of the wiring that joins these things up. And so we might say that in this truth table, basically, whatever the previous value of Y was is maintained. And so this type of gate is called a state-holding gate because during some phases of operation, the state is held by the gate, or has to be remembered by the gate. And this type of gate is actually called a Molar C element. Sometimes called a consensus element. And its basic use is that basically the output only transitions in a given direction when all of the inputs have made a transition in that direction. So the output of the gate signals when the inputs to the gate have come to consensus. And so the symbol that's typically used for this gate is something that looks like this, where you have a C inside a circle, and you have A, you have B, and you have Y. And this is commonly used in asynchronous digital systems, where instead of having a clock that sequences all of the various operations all the various operations and data transmissions, when you have an asynchronous system, which is a system without a clock, you basically have to detect when things are done when things are completed, computations are completed, data transmission is completed locally, and you have to communicate through what are called handshaking operations. And this type of C element is used for ensuring that, or detecting when like all of the basic operations in a given computation have finished, by waiting for all of its inputs to come to consensus. Now this, as it stands right here, would be a dynamic version of the Molar C element, where, as I mentioned, the state is held on whatever parasitic capacitance happens to be on this internal node here. And that's kind of precarious, especially in a system where you may have to wait for an indefinite period of time before you proceed until your inputs come to consensus. And so one way of taking this dynamic gate and making it into a static gate where the state is actually held statically in a stable operating point of the system is to add what's called a staticizer, which is a little feedback inverter around this inverter here. So this whole gate is called the Molar C element, and this little inverter here is called a staticizer. And its job is basically a feedback, so this is a feedback inverter that turns the dynamic state holding gate into a static one. So we basically have made a bistable element here by adding this extra little feedback inverter. And this is typically a weak inverter, which means the devices are tall and skinny, meaning that they have a long length and a narrow width. And that's because we can have a writability problem in this structure. You can imagine, especially when I have these two PMOS transistors in series here, fighting against the single NMOS transistor in this pull down of this feedback inverter, these two PMOS transistors in series may have a hard time overwriting or overpowering that feedback inverter unless we make this feedback inverter quite weak. There are ways of basically cutting off this feedback inverter by putting appropriate transistors in series with it, but oftentimes what's done is just to make these devices quite weak compared to these devices here in the C element. Okay, so that's an example of a state holding gate that actually is used quite a lot, especially, like I said, in asynchronous digital circuit design. There are other ones that one could talk about, but my purpose here was just to kind of give you an example of one that's very commonly used in practice, and it does have this state holding property. So I think that's about all I'm going to talk about in this particular segment. We'll probably do a little bit more with digital stuff before we switch gears and go back to analog stuff. But we're almost to the end of our little foray into digital CMOS design.